Hello. In this session, I'm going to speak to you about how to examine relationships amongst variables in your data. We're going to talk about here using techniques of correlation and regression to examine relationships amongst variables in our data. We'll go over what correlation is, examine regression. Under regression, we'll talk about the mechanics of estimation, prediction and inference, and then examine the various types of regression, including simple regression, multiple regression, and automatic variable selection. We will illustrate each one of these techniques and aspects of examining relationships using a couple of examples. Correlation is a measure of an association between two variables. If one variable changes when another changes, the two may be said to be associated. Correlation is a bidirectional relationship. It is typically indicated using a double-headed arrow to indicate there is no directionality to this relationship, or you can say it's bidirectional, that is, it can go either way. There exists a number of measures of correlation. When working with nominal scale data, one can examine something called a contingency coefficient. With rank order data, one can examine a Kendall's rank correlation. Pearson's product moment correlation is by far the most widely used metric for measuring correlation. It applies specifically to interval ratio scale data. Other measures include cosine similarity. Our focus here is going to be on the most common flavor of correlation called Pearson's product moment correlation. A couple of things to remember about this method or measure is that it's a measure of linear association between a pair of variables. Thus, two variables may be non-linearly related, and if so, Pearson's product moment correlation will not pick up the full extent of that association. Mathematically, correlation can be measured as standardized covariance. That is, in the formula, the numerator includes the product of the deviations of the two variables from their respective means, divided by the product of the variances of each of the two variables. Thus, correlation can be called or seen as being standardized covariance, standardized by the individual variances. Thus, correlation, unlike covariance, has a nice bounded range of -1 to +1, where -1 indicates the absence of a perfect negative relationship, +1 a perfect positive relationship. 0 indicates the absence of a relationship. Since our goal typically is to draw inferences about the population, 1 denotes the population parameter for correlation as rho. Our goal is to infer population correlation from sample correlation. The hypothesis tested for correlation is as follows: HO or H0, rho is equal to 0, or there's no relationship between X and Y. H1, rho is not equal to 0, or there is a relationship between X and Y. We typically assess this using a t-test. If the test is significant, then one rejects HO and concludes that there exists a significant relationship between X and Y. The range of X of R is -1 to +1. In addition to these bounds, that is -1 is perfect negative, +1 is perfect positive, 0 is absence of correlation, one can also think of some heuristics to assess the strength of relationship that isn't quite perfectly negative, perfectly positive, or non-existent. A range of -3 to +3 is seen as being weak, -3 to -0.7, or +0.3 to +0.7 as being moderate. And lastly, anything less than -0.7 or more than 0.7 is seen as being strong. These are merely heuristics of strength of relationship. Now, let's get a sense of what correlation is by examining some plots. Given here are a couple of scatter plots. A scatter plot is the most natural way of examining the relationship amongst two variables. One can place the two variables on x and y axes and present the data using dots. The distribution of the dots on the scatter plot indicates the existence or lack thereof correlation. In this case, you can see the pink dots are nicely grouped together and they're trending in a certain clearly specified direction. They're going from bottom left-hand corner to top right-hand corner. Whenever your scatter plot looks like this, you can safely assume that there is a fairly strong correlation in play. Quantitatively here, Pearson's product moment correlation is 0.98. Indeed, the correlation statistic supports our intuition of this being a strong correlation. Next, we look at another chart here where, as you can see, the relationship is not linear. The points are still going from bottom left-hand to top right-hand, but not in a linear path. Since correlation, or Pearson's product moment correlation, captures linear association, this correlation coefficient isn't quite as high as the previous one. The relationship is fairly strong, however, not linearly strong. Correlation is 0.96. Going further along here, here's another example of a scatter plot. In this case, yet again, the dots go from bottom left-hand to top right-hand. Whenever the data is trending from bottom left-hand to top right-hand, you can safely assume the relationship is positive. However, here again, the trend through the direction of the points is a bit nonlinear, telling us that this was also not going to be a perfect correlation. But yes, it is still indeed a fairly high correlation of 0.93. In this graph, the data is going from top left-hand to bottom right-hand. Whenever your data looks like this, you can safely assume you've got a negative correlation between the two variables. That is, as x goes up, y is going down. And that's what a negative correlation means. Furthermore, you'll notice these points aren't linear. And again, therefore, you see that that penalty that you see whenever your data is associated, but not linearly, Pearson's product moment correlation won't be quite so strong. So you have here a minus 0.7, which based on heuristics is strong, but not as high, as big as the numbers we saw in the previous slide. Finally, here is a scatter plot showing a set of dispersed data. There's really no clear trend to these points. They're just all over the place. They're jittered or scattered all over the place, telling us basically here there's no trend, or as x goes up, y doesn't change proportionately or in a consistent manner. And therefore, here one would suspect there being a very small correlation. The correlation here is minus 0.06, very close to 0. Let's move on and analyze and examine correlation using an example data set. The data set we have here is our territory sales data. We have data on territories of a company. This company has many territories, but we only have data on 40 territories because the cost of getting complete data was large for this company. For every territory, we have the sales in thousands of dollars. We also have the advertising, extent of advertising for every territory. This was hard to gather because it is hard to know who in a given territory is watching a certain TV ad. Nevertheless, after some careful analysis, they were able to figure out how many TV spots were shown in a given territory in a given month. And that's what advertising refers to. Number of sales reps or reps is the number of sales reps assigned to a territory. That's an easy number to get. Lastly, wholesale efficiency index is a measure of the wholesalers in the area. This is measured as a rating. So it's a rating from 1 to 4, where I'm reading off the data description out here. 4 refers to outstanding, 3 to good, 2 average, and 1 is poor. So a higher number would indicate a higher wholesaler efficiency index. So we have here 1 sales variable and 3 variables you would expect or imagine would be in some way related to sales. Let's begin by examining relationship between sales and advertising. I'm going to switch from the PDF to slides so that I can easily annotate the slides. Here's the switch. We go from the PDF over to PowerPoint slides. The question here is there a relationship between sales and advertising? So our null hypothesis is going to be there is no relationship between sales and advertising. But let me cheat a little bit. Let me go back to previous slide, and I will take this exact hypothesis and modify it. Modify the language, that is. So we understand that the hypothesis represented here is simply adaptation of the general hypothesis. It's messing up my formatting here a little bit. So let's see if I can get the formatting to look nice or nicer. Okay. This isn't quite cooperating with me too well. So let's go back to what we had before. And okay, so here we have H0 and H1, which is the generic hypotheses, rho equal to 0 and rho equal to rho not equal to 0. So our HO is there is no relationship between X and Y, where X is going to be advertising and sales. It doesn't matter what we call X and Y because we're looking at correlation. But I just have a habit of representing what we expected to be the cause as being X and the effect as Y. Okay, so that's our hypothesis, HO and H1. Our first step is going to be to construct a scatter plot to examine the relationship. A scatter plot is a handy method to examine the relationship amongst any two variables. Let's switch over to our data set next. Our data set is the territory sales data, which I'm going to load in SPSS. Here's the data, territory sales.sav. In here, you're going to notice the columns, territory, sales, advertising, reps, and WEI. Under variable view, we'll review a little bit more about the variables. I've labeled these variables. So we have here sales is sales in thousands of dollars. Advertising refers to TV spots per month, reps, number of sales reps, and WEI is the wholesale efficiency index, which is really a ordinal scale data, but we'll represent that as being scale out here, despite the fact that it can be argued to be a ordinal scaled or rank ordered data. But we're going to keep that as interval scale here. Okay, let's go and examine the correlation. To examine the correlation, you go to Analyze, Correlate, Bivariate. We want to examine correlation between sales and advertising. We'll select those two variables and bump them to the right under variables. And that's it. Click OK. Let's switch over to the output window to examine what happened. Here's our output from running that analysis. As you can see out here, we have a 2x2 matrix. The correlation of two variables looks unnecessarily complicated, as represented here, but that seems like the norm. I say so because if you look carefully, we have here sales and advertising on the x-axis and sales and advertising on the y and x-axis. So in this crosstab, we have basically sales and advertising in both rows and columns, which basically means we have some data that's almost redundant. If you look carefully here, you have a 1 here because this 1 represents the correlation of sales with sales. And the 1 in the bottom right-hand corner represents the correlation between advertising and advertising. No surprise that that's 1. Correlation with oneself has got to be 1. What we really care about here is the relationship between advertising and sales. That's this number here. Okay. So our correlation turns out to be 0.880. That's what our R is. You'll also notice we have another number on the top right-hand corner, which is, again, the same number. This correlation is a bidirectional relationship. It doesn't matter whether you examine X to Y or Y to X, they're the same thing. Bottom line, when you're looking at a correlation matrix, you can safely ignore some bits of the matrix. If you want, all you can do is fixate on one section. My personal habit is to look at either the top, at the elements above the diagonal or below the diagonal. In this case, the diagonal I'm referring to as the sets of ones. In a correlation matrix, the diagonal always has ones. You can decide to go below the diagonal, then that's focusing on this number here, or the one above. It's good to pick a norm and stick with it, so it's not a hard and fast rule. You don't. It's more of a, again, a personal preference here. Do you want to look at what's below the diagonal or above the diagonal? But just pick one of the two so you can be consistent with yourself. Okay, so here we have our correlation coefficients being 0.880. What we do know is that our R is 0.880. And furthermore, we have right below our R, a correlation coefficient, a p-value. We've been told our p-value is really small, it is less than 0.001. Whatever that small number is, it's less than 0.001. We're also given that N, our sample size, is 40 observations. Let's put this in context then. Okay, so let's go back to our slide. Our correlation is 0.88, and our p-value is less than 0.05. Less than 0.001 is definitely 0.05. I'm going to say 0.05 compared to that because that's our alpha level we set before the fact. Based on here, so it's safe to here to rule out HO. You can safely reject the null hypothesis of no relationship. And as far as the strength is concerned, if you look back to the heuristics, the fact that this correlation is above 0.7 is telling us relations are strong. Okay, so there is a strong relationship. There exists a strong relationship between advertising sales. Now, in my haste to compute the correlation, I completely neglected to run this to examine the scatter plot. No worries. Let's go back and do that right now. We already know that there is a strong relationship. So let's look for a scatter plot that represents a strong relationship. Here is the correlation information. When you go to graphs, under graphs, there are two options. You can go to legacy dialogues and look for a scatter plot. Select simple scatter, move advertising to the x-axis, sales to the y-axis, and that's it. Here's what you get. Now, in a bit to catch up with the other software that I've got really good graphics capabilities, SPSS has tried to make their graphing options more exciting. So another way of constructing the same scatter plot would be to go to graphs and then select chart builder. From here you can select a type of plot. I'll pick scatter and then drag the scatter plot that I want into the window on top. And then where it says x-axis and y-axis, we'll drag and drop variables that we want to express. With that done, hit OK. Here's our scatter plot. The picture is the same, regardless of whether you use this one here or use the G graph, as we call it. Okay. All right, let's look at the picture then. Let's focus on the picture here. The picture is telling us that as you look at the data, there's a clear trend to it. The data is trending from bottom left hand to top right hand in a linear way. This is telling us that there's clearly a linear relationship or positive linear association between X and Y, advertising and sales. And we can also tell that since the points are fairly, together and they're pointing in a clear direction, the relationship must be fairly strong also. And that's borne out by a correlation coefficient and the fact that the p-value is less than 0.5. Okay, so we've examined the correlation amongst sales and advertising. Let's move along and repeat this for sales and number of sales reps. Specifically, we're looking to say whether there's a relationship between territory sales and number of sales reps. So HO, there is no relationship between sales and reps. I'm going to keep it short here. And that's same as saying rho is equal to 0, or we don't have to say that really. We make a choice of whether to say rho equal to 0 or write this whole expression out. I'm going to do both in the interest of completeness. There is a relationship between sales and reps. Okay. This time around, I'll do it the right way, and I'm going to make the scatter plot first before examining the correlations. Let's go over to our output window, or rather our data window. Here we are. We've got sales here and reps here. We want to see if as number of reps goes up, does sales go up for us? In other words, if you've got a large number of reps, is that in any way associated with greater sales? So analyze, correlate, bivariate. And then we'll move sales reps where advertising was before. Okay. And hit OK. In the output window, we will examine, I'm sorry, I did that again, didn't I? I meant to do the scatter plot. So let's do scatter plot first here. So graphs, we'll do chart builder to assign a different method for making our scatter plot. And we'll drag over here. Oops, let's reset this thing. Drag over scatter plot and drag over sales to Y, sales reps to X. That's it. So you can see out here, we have here sales reps is like a discrete variable, somewhat discrete variable. Well, this is a discrete variable because you can only have a certain number of sales reps. You can have 3, 4, 5, 6, 7. You can't have 2.5 sales reps for a territory. And for that reason, you're seeing this sort of like this nice grouping of these sort of like binned data points, right? So kind of see these nice bins showing up here. Okay, so that kind of makes sense given the nature of the variable being discrete. But overall, a trend, if you look carefully, is to go from bottom left hand to top right hand, which is telling me that we clearly have a positive relationship. The second thing that should be obvious to you is that the line is pretty close to all the points, and the points are quite kind of like nicely lined up on oriented on a straight line, which should be telling you that this must be a fairly strong positive relationship. Let's examine the correlation right now. I'm going to analyze, correlate, bivariate, and I'm going to say OK. It was before, but I'll do it again now. So here we are. Our correlation stats are right here. As before, as I noted in the last for the last analysis, I'm going to ignore what's above the diagonal. So I'll just only focus on what's below the diagonal. Let's focus on what's below. Forget about what's above it. X all this stuff. Don't care about this stuff. Okay. So focusing on our stuff below the diagonal, here is our focus. Our focus is on this little section here. So looking at number of sales reps and sales, it is obvious that the correlation is 0.882. That correlation has a p-value of less than 0.001, which clearly would be less than 0.052, and a sample size of 40. Let's go back to our slide then and make note of these numbers. So our correlation coefficient is 0.882, and our p-value is definitely less than 0.5. So clearly, we would reject the null hypothesis of no relationship. We'd say the relationship is strong. There is a strong relationship between reps and sales. Number of reps. Okay, so this is how you examine a correlation between a pair of variables. Now, in practice, correlation is an extremely useful technique to examine relationships amongst not just a pair of variables, but many pairs of variables. Sometimes folks will take a whole bunch of variables and just throw them into a correlation matrix to examine associations of all variables with each other, almost using it for some sort of exploratory analysis. Moving along, let's examine. So yeah, a correlation matrix is a common practice. Folks will just throw in a whole bunch of variables together in the correlation matrix. Let's see what that would look like in our context here. So you might just say that you want to go to analyze, correlate by variable, and just say, let me put all the variables in and get one large correlation matrix out of this. We'll get to that pretty soon. For now, let's move along to our next topic on partial correlations. There are situations where you might want to examine the correlation between two variables after controlling for, or adjusting for, or teasing out the effect of some other variable. So mathematically, that's the formula for partial correlation. We're taking out the effect of z from in examining the relationship between x and y. So you can think about partial correlation of having an order associated with it. The order depends on how many variables are being partialed out in constructing the correlation. So the common research question might be, is there a relationship between two variables after controlling for a potential confounding variable, a variable that's like a monkey wrench in the relationship? Or maybe it's felt that the two variables are related together because of some other hidden unknown variable, and that's sort of like why I want to control for that statistically. So just to kind of illuminate this idea here, two variables might go up in lock sync because they're affected together by a third variable. So a classic example or illustration to this point is the observation that consuming ice cream is highly correlated with drowning in a pool. So again, consuming ice cream is highly correlated with drowning in a pool. Yeah, clearly, this doesn't seem reasonable that eating a lot of ice cream should, cause somebody drowning in the pool. If you use control for weather, you'd find out that the relationship would vanish. Specifically, the one thing that connects both eating ice cream and swimming in a pool, the one kind of variable linking the two together is summer. In summer, people eat a lot of ice cream, and in summer, people go out swimming in pools. People go swimming in pools, the odds there'll be drownings are higher than if they weren't swimming in a pool. So in a sense, the weather here is a confounding variable. And if you could partial it out, you get a more pure assessment of the relationship between two variables of interest. Here, we're going to go on to examine the relationship between territory sales and advertising after controlling for number of sales reps. If one is suspicious that, territory sales are high because of advertising, and maybe somebody's skeptical about the idea that maybe it was not advertising that's tied to territory sales. Maybe it's the fact that there's some other third variable here that's playing a role out here. Maybe it so happens that places where they have more advertising, there are also more sales reps. And so it's really, if you take out the effect of sales reps, it's possible that the effect of advertising on territory sales might altogether vanish. So we're really testing out here the purity of a robustness of the relationship between advertising and territory sales. To do this, here's what we can do. We're going to go back over to SPSS and we'll examine how robust this relationship between sales and advertising is by controlling for reps. So analyze, correlate. Now we'll go to partial. Under partial, we can select variables we want to connect or link together. Here are sales and advertising. And then we'll select the variables we want to control for. We want to control for number of sales reps. Let's move that into the right and click OK. You switch over to the output window now. Here you'll notice in the lower panel, we're going to focus here on the bottom left-hand corner of this matrix. We got to pick one square to look at. That number is 0.658. Now, if you look at this number for correlation, clearly this is a, it's a correlation that's well above zero. In fact, the p-value tells us it's significantly different from zero. And you would argue this is between the 0.3 to 0.7 range, so a moderate size correlation. Clearly, advertising has an influence on sales even after controlling for number of sales reps. You may recall the correlation when we weren't controlling for sales reps was about 0.86 or so. So we have seen when you went from, let's go back and find that actual number that we had before. So here's the number we had for advertising and sales, 0.88. So we've gone from 0.88 to 0.658, 0.88, which was sort of like 80, sorry. When we weren't controlling for correlation, 0.80, and now 0.658. So we're seeing then sort of like in a sense, a attenuation correlation. This is telling me that sales reps did have a role to play, but it doesn't take away from the fact that advertising, even after controlling for sales reps, is an important, associated variable for sales. Okay, so we examined here partial correlation. There's also something called semi-partial correlation you can look at. Okay, semi-partial correlation involves partialing out the effect of the contaminant variable from one of the predictors, one of the independent variables, so to speak, but not from the dependent variable. Thus, it looks like a regression coefficient. Since I mentioned regression coefficient, maybe you should look at regression next and examine semi-partial correlation from regression lens. And that'll be the next topic we'll look at.